Lecture 6, Probability. So building off our previous lectures that talked a lot about mean and standard deviation and the unit normal table, we are going to build on that today. We're going to talk about probability. So we will start off with what the definition of probability is, and then some of the assumptions of random sampling, definitely talking about the unit normal table, the z-table, the, right, whatever you want to call it. And I gave you the PDF for that. If you find it on Google Images, that works as well too. So how do we use the unit normal table to find probabilities? How do we use the unit normal table to find scores for proportions, and then finding percentile ranks in normal distributions? So some things to keep in mind when we talk about proportions. So definitely fractions, decimals, percentages, all that type of stuff. Obviously your basic algebraic functions, formulas, equations, everything to do with z-scores that you've learned up till now, a little bit of your DF, so your degrees of freedom, all of your formulas, right? So formula for both population and sample, all your rules that govern z-scores, and then everything that we've learned up until now with your unit normal table, again, the flow and function of it and the purpose of it. Okay. So just kind of a broad overview with probability, right? So all research begins with a general question, right? Something that we want to learn more about, usually about a population, but we don't have access to a population, so we grab a sample. So the actual research usually is done with a sample. And so we take a group, right, from that population, and then we gather data, right? And we gather inferential statistics, right? We use that sample data, and we use what we learn from that sample to infer then back to the bigger population. And then we look at some relationships, right? We look at relationships between the samples and the populations. And then, we take a look at how sure are we, right? What's the probability that we can say, what we did there, that treatment was effective, that medicine was the thing that cured them, or that exposure that we did to that sample was the actual thing that worked, and we can then infer that back to the greater population. Okay, so again, you have this kind of teeter-totter back and forth kind of thing going on there, right? So the role of probability in inferential statistics is to make that link, right? So we have a population. We don't usually have access to the entire population, and if we do, we don't really have the resources to the time and money and people needed to test an entire population. So we grab a sample, and then we test the sample, and we learn something about the sample, and then we infer what we learned from the sample back to the population. And then we say, okay, based on what we learned from that sample, how realistic is it? How sure are we? What's the probability that we can say, yes, definitely, or most probability, most likely that it was that treatment that our researchers, that our statisticians predicted that was the treatment. Okay, so probability is used to predict the type of samples likely to be obtained from the population, right? So probability really does help to establish that connection between samples and populations. Okay, so inferential statistics relies on this connection when using sample data as basis for making conclusions about that population. Okay, so that's what we're really going to focus on in today's lecture. So mathematically and linguistically, how do we define probability? Okay, so mathematically, probability of A, so event A, so whatever you want to kind of look at there. So mathematically, it's the number of outcomes classified as A, whatever you want to study, divided by the number of possible outcomes. So if I'm flipping a coin and it's head versus tails, and I say, okay, what's the probability of getting heads, right? Well, if I know my total possible outcomes is heads versus tails is 2, and I want to see what heads is 1, so 1 divided by 2 is 50-50. I have a 50% chance, or 0.5. Okay, so when several different outcomes are possible, the probability of any specific outcome is a fraction, proportion, decimal, right, probability, right? Just a little bit of all the possible outcomes. Okay, and that's what we're going to be talking about today. So we used that little sigma, right, the little circle with a curlicue on top, as our symbol for standard deviation, right? And df, so the slanty d and the slanty f, for degrees of freedom. P, or a little slanty p, is a symbol for probability in statistics. And probability of some specific outcome is specified by a p, and then in kind of little brackets there, event. So what's the probability of whatever event you're looking for? Okay, so the probability of drawing a red ace from a standard deck of playing cards, all right, so you've like, okay, you have to think, okay, what's the standard deck of playing cards? Well, in today, 2024, or mid-2020s, right, well, when you think about, okay, what's a standard deck of playing cards, well, you have 52 cards in a deck, and you have some that are like face cards, so you have the king and the queen, and the right, and then you have some that are number cards, right? So you have like a 4 and a 7, and then you only have certain ones that are aces, right? So you have a couple aces that are black aces, and you have a couple aces that are red aces. So if I'm looking at specifically drawing, what's the probability of drawing a red ace from a standard deck of playing cards? Okay, so how I would write that in a probability statement, it would be P, like the little slanty P, and then in parentheses, red ace. Okay, and keep in mind that probabilities are always written as proportions, because I'm looking at what's the proportion of all the possible outcomes. Okay, so P, red ace, is 2 divided by 52, because all my possible outcomes, right, is 52. Because if I have a standard deck of cards, there's 52 in there. But I only have 2 chances, if you will, to get a red ace. I can get a red heart, right, ace, or a red diamond ace, right? Okay, so if I take 2 and divide it by 52, I get 0.03846. Okay, so pretty small chance, pretty small probability. Okay, random sampling. Okay, a sample is obtained by a process that has to ensure a few things. Okay, first thing, everybody in your group, everybody in your study has to have an equal chance of being chosen. Okay, you can't look at somebody and say, they look like they're going to take to the treatment pretty well, or the opposite, they don't look like they could ever be broken, or the treatment's never going to work on them. No, everybody in that group, everybody that signed to be part of your study, everybody that you kind of grabbed you part of your group, everyone has to have an equal chance of being selected. Selected as the experimental group, selected as the placebo group. Okay, this is known as just simple random sampling. Okay, the probability of being selected must also stay the same or constant from one selection to the next, even if you are constantly choosing from that same bucket, if you will. Okay, this is also known as independent random sampling, which then requires sampling with replacement. Okay, yes, random sampling is required for our definition of probability to be accurate. Okay, now take a look, far right hand side there. It says the term independent isn't usually stated out loud, so it's typically omitted. So it just usually becomes random sampling, or just random sampling with replacement. Okay, so let's tease this out a little bit more. Okay, so when we talk about random sampling with replacement, or I guess the long linguistical technical term would be independent random sampling with replacement, or how we just usually always refer to it as just random sampling. Okay, so if I have a hat and I put 30 names in the hat, the first name I pull out is randomly sampled, randomly chosen, randomly selected. Every person's name in that hat had an equal chance of being chosen, right? Because I'm kind of mushing my hand around in there, and right? And I just kind of pull a name out. Okay, and Miguel's name gets pulled out of the hat. Because everybody had a 1 in 30 chance of their name being pulled out. And if I take Miguel's name and set it to the side, and then start swirling my hand, right, in the hat again, it's not the same chance of being selected. Okay? Because if you take out your calculator and you say, okay, 1 divided by 30, which is what the odds were whenever Miguel's name was in the hat and I was swirling my hand around. And I guess, okay, Miguel, you win the first prize, right? And I take his name and I put it outside. Now I'm putting my hand in the hat again. Now your odds of being chosen, your name being pulled out of that hat, is now 1 divided by 29. So it's not the same chance as being selected, right? So when we're saying the probability must stay the same, even when the odds are being changed because names are being constantly pulled out. That's what we're saying there with the requires sampling with replacement. I have to put like a dummy name in or a neutral name in. I should call it a dummy name. All right, so if the rules are Miguel can't win twice, right? So if I can't put Miguel's name back in the hat, because that would level the playing field again, right? So 1 out of 30 chance, right? So if Miguel can't win twice, I take Miguel's name out and say, okay, Miguel, here's your candy bar or whatever you win. I have to put a non-name in or a neutral name in, because now everybody has a 1 in 30 chance of winning again. That's sampling with replacement. Okay? Because after a while, and if you're like, well, what's the big deal? Like 1 out of 30 versus 1 out of 29, it's not the big of a deal. Yes, but keep it going, right? So say then Maria wins, and then John wins, and then Susie wins, and now you're down to like 1 or 2, right? It's between you and, I don't know, Lucy or whatever, right? Now you got a 50-50 chance. That's totally not fair. Right? Because Miguel had to beat out like 29 other people. He had a 1 in 30 chance, and now all you have to do is a 1 in 2. That's 50-50. So if you are going to be taking out people, you have to be putting dummy names back in or neutral names back in. So sampling with replacement. Probability and frequency distribution. So think back to like lecture 2, right? So probability usually involves dealing with a population. Absolutely. And then we need to use it with a sample, okay? Displayed in a frequency distribution graph, meaning when you're dealing with a population, you know a lot about the mean, you know a lot about the mode, you know a lot about the median. Think items that we know a lot about, IQ scores and blood pressure and pass-fail rates of English 101 classes, right? Thousands and thousands of scores. Okay. Different portions on the graph represent different portions of the population. Now here's the kicker, right? In most things, as long as you're getting a really good representative sample, like you're not cherry picking your data, when you get to around 30, you're approximating a population mean, meaning humans are not that wildly different from each other. And as long as you are truly getting a representative sample, like you're not being weird about the samples that you're gathering, you truly are authentically just going out and getting a pretty good sample, like a cross-section of people, your proportions, your probabilities, your proportions, your proportions, your mean, your mu, your samples, your populations, they're going to approximate the same. Okay. So a particular portion of the graph corresponds to a particular probability in the population, just like a sample does. Okay. So let's take a look at here. This is a histogram. And again, you know it's a histogram because the lines are touching. Same thing. Frequency distribution, the height of the bars correspond to the counts, right? How frequent or how many of your people are getting that score, okay? So this is a frequency distribution histogram for a population of 10 scores, okay? So you had 2 people that scored a score of 1, and you have 1 that scored 2. Your highest number there, your highest scoring or your most frequently scored number was a 4, because you had 3 of your people score a score of 4. Okay. The shaded part of the figure indicates the proportion of the whole population that corresponds to a scores greater than 4. Okay. So if you're doing a test and you're saying, okay, I'm going to see who's going to be on the varsity team for, I don't know, high jump, right? And I'm the coach for the high jump team, and I say, okay, anybody that can jump higher than this measurement on the bar, you're going to make the varsity team. Okay. And I can do my frequency distribution chart there, and I can see, okay, 2 of my athletes did. They did a 5 and 1 did a 6. Okay. I can also understand what I'm going for, because the shaded part, or my 2 qualifiers there, is 2/10 of the whole distribution. So what I'm telling my athletic body, what I'm also telling my probably athletic director, right, is I'm looking for the top 20 percenters, right? And so if you scored in the 4 range, you know for next year, okay, I'm this close, right? I just need to get that much higher in my high jump. Okay. That's the power of a z-score. That's the power of ranking against means, right, or averages. Okay. Okay, so quick learning check. A deck of 52 cards contains 12 royalty cards. So think like the kings and the queens, right? Okay. If you randomly select a card from the deck, what's the probability of obtaining a royalty card? So a deck of 52 cards contains 12 royalty cards. If you randomly select a card from the deck, what's the probability of obtaining a royalty card? Again, P equals whatever the event you're looking for, divided by all the possible outcomes. Okay, so we know currently in our standard playing deck, right, we have 12 possible guys and gals that qualify as royalty. So 12 divided by all possible outcomes, because you could pull a 2, an ace, a 10, right? Okay, true, false. Choosing a random individuals who walk by you yields a random sample. So true, false. Choosing random individuals who walk by you yields a random sample. False. Okay. Not all individuals that walk by you have an equal chance of being selected for the sample. You are not a cross-section of the world. You are quite individualistic in your demographics, right? In your socioeconomic status, in your, I don't know, education level, in your gender makeup, in your everything, right? So when I say you have to authentically get a good cross-section of humanity, you just sitting where you normally sit isn't probably going to yield you a good random sample. Okay. True, false. Probability predicts what kind of population is likely to be obtained. I shook my head, sorry. So false, yeah. Population is given. Probability predicts what kind of sample you're likely to be obtaining, right? So the population it just is. You can't really manipulate a population. Population is. What you're looking at with the probability, sorry, I didn't mean to shake my head there. I was like, no. Probability is trying to tell you how good of a sample are you really pulling. Okay. Let's talk a little bit about probability and the normal distribution, right? So normal distribution is a common shape. Again, it's that, right? It's that normal curve. It's that bell curve, right? It's symmetrical. Whatever's happening on the left-hand side is happening on the right-hand side. The highest frequency peaks in the middle, and it kind of dips down, right? The frequencies taper off to the 2 tails at the end, okay? It's absolutely defined by the equation. The equation changes a little bit depending if it's a population or a sample, right? It can be described by the proportions of the area contained in each section. And how do we determine that? Well, we determine by the z-scores, okay? Using the normal table. Okay, so here it is. Don't freak out about the equation in the top right-hand corner there. That's just the mathematical constants, right? Pi and E are mathematical constants. So yes, this is another way of looking at it. No, it's not going to show up on a test or even after the slide. It's okay. This is just showing you the mathematical equation of this area, right, of the normal distribution. Okay, normal distribution is the exact shape of the normal distribution is specified by an equation relating that each x value, each score, with each y value, the frequency. Okay, so again, x is that score on the bottom or the right to left, the horizontal line. Okay, all of us in a population will yield a score, right? How tall we are, how much we weigh, what our blood pressure is, what our IQ score is, right? Then, depending on how popular our score is, how much we have in common, right? If you have that exact same score I do, and if we have the exact same score as 1,000 other people do, that's how much it's going to be, how tall it is. That's the frequency of it. Okay. Graphically, or what it looks like visually, right? The normal distribution is symmetrical. It's got one mode right in the middle, right? It's got one mean. It peaks, right, at the very, very middle, and it tapers off. And if you, at the very, very ends, right, the two tails. So if you think back to, I don't know, lecture 2 or 3, and we talked about skewness, right? And I said, I know it's silly, but if you think about it like the body of the elephant is like the big bulk of the data, right? And where the tail of the elephant points towards the number line, that indicates if it's positively skewed or negatively skewed. Okay, same premise here. The bulk of the data, the body of the elephant, is still the biggest part. The biggest part now is just in the middle, right? Meaning the bulk of the data, the frequency of the data is piling up in the middle. Now we have two tails. Okay. Now we are going to talk about running a one-tailed test and a two-tailed test. The only thing we need to keep in mind with a one-tailed test is you're pretty sure what you're going for. Two-tailed test, you know you're going to have an outcome. We just don't know if it's going to be up or down, good or bad, more or less, right? Meaning, if I have a hypothesis about something, and I know if I add salt to someone's diet, I'm going to increase their blood pressure. That's a one-tailed test, because I'm using words like increase, up, more. Okay. If I have no idea what adding magnesium is going to do to someone's sleep cycle, I run a two-tailed test. Because I have a hypothesis, it's going to have an effect. I have no idea if it's going to increase their sleep levels or sleep time or decrease their sleep time. Okay. So when we're talking about tails, think the very tippy top ends, right, of the distribution. Okay. And it's still symmetrical, meaning that single mode right in the middle, that single mean, right, that peaks the very, very top. Okay. Same thing with those tails. They're the same. They take up the same amount of space, meaning frequency-wise, the same occurrences happen. They just taper off really, really quickly at the end. Okay, let's talk about how quickly. Okay, so we take a look here. Again, when we convert it from a raw score to a z-score, the mean turns into 0, and the standard deviations turn into 1. Okay, so if we're going to use IQ as our example, average IQ score is 100 with a standard deviation of 15. If I convert it to z-scores, the average z-score for an IQ is 0. So if I have an IQ score of 100, my z-score is 0, meaning I'm perfectly average. I don't deviate from the mean because I am perfectly average. I don't deviate at all. I'm right on the center. If I have an IQ score of 115, I am 1 standard deviation above the mean. And because it's symmetrical, meaning what happens on the right-hand side happens on the left-hand side. If I have an IQ score of 85, I'm also 1 standard deviation away from the mean, but now I have a z-score of -1. Okay. Percentage-wise, 68.26% of us fall between -1 and +1 z-score all the time from the mean, regardless of whatever thing we're talking about. So in this case, IQ scores. Okay. So let's put the raw scores back in. In other words, 68, and all I'm doing is adding up 34.13 below the mean, right? So out of all the humans walking around the world, 34.13% have an IQ score of 85 to 100. Also, 34.13% of humans have an IQ score of 100 to 115. You can add them together too. If you add them together, 68.26% of us, of all the humans in the world right now, have an IQ score falling somewhere between 85 and 115. Isn't that wild? That's most of us. In fact, 68% of us, that's the big bulk of us, right? Watch how fast the percentages start to taper off on both sides. 13% of us have an IQ score of 115 to 130. Because again, a z-score of +1 to +2 correlates between an IQ score, raw score, of 115 to 130. Also, because it's symmetrical, 13.59% of us have an IQ score between -2 and -1 z-score. Right? Because again, what happens on the right-hand side happens on the left-hand side. And then watch how fast the percentage drops again. 2.28 on both sides. Okay? So like I mentioned, I think in last week's lecture, in every state of the union, we give all second graders an IQ test. And what the IQ test is looking for is the ±2, the cutoff's there. Okay? For a couple different reasons. If you don't catch them, they will fail out at the same rates. And you think, well, if you have an IQ score above 130, you won't fail out of school. Yeah, you will. Yeah, because it's going too slow. You're smarter than the teacher. That type of stuff, right? And then if you have too low of an IQ, you need remediation. We don't call it remediation anymore. We call it different words. Okay. Now, again, the note of feelings, we don't say -2 because that would not be kind to second graders. We also don't say +2 because, well, feelings again, and second graders are wild about honesty and transparency. Okay. So, and z-scores do go to infinity, but as you can see how fast the percentages tapered off. I mean, it went from like 34 to 13 to 2, right? I mean, it goes, sure, in theory it goes to infinity. In practicality, you're rarely going to see one past 3 because we're like point numbers after that. Okay. So humans fall into this distribution both physiologically, so things like height and weight and blood pressure and that type of stuff. We also fall into this distribution with psychologically, so specifically with personality types, things like obedience and compliance, things like that. Not wild when you think about it. Okay. Some of the characteristics, again, I know I'm hitting this ad nauseum, but it's very important. Sections on the left-hand side have the same areas, correspond on the right-hand side. Think mirror image, think symmetrical. Z-scores are defined as sections and the proportions of the areas that apply to any normal distribution, regardless of the mean, regardless of the standard deviation. Okay. You can also use this for distribution of the SAT score. So in this one, this is the math SAT score. So the average or the mean is 500 with a standard deviation of 100. It used to be that we looked at SAT scores for raw intelligence. It's not, we still use SAT scores for certain markers. It's no longer for raw intelligence. It's other markers now, which is fine. But it's not for raw intelligence. And then, so if you score in the 700 range, what we're saying is, yes, you're good at math. You're good at scoring well on the math assessment. But more than that, you are 2 standard deviations above the mean better than your peers in that year in math. Or another way you can say it, only 2% of the people that took the test in the same year that you took the math test, or the SAT math test, scored better than you. Or another way, you scored higher than 98% of everybody else in the country. Okay. Some other points about the unit normal table. The proportions for only a few selected z-scores can be shown graphically, right? Like, you can write 0 and 1 and 2, and on the left-hand side, -1 and -2. You can even do like 1.5 and -2.25. But you can only do like so many, right, before it gets crazy town. So you can't do them all. So that's where we have a graph, right? So the complete listing of the z-scores and proportions provided in the unit normal table. The table lists proportions of the unit normal distribution, full range, down to like 0.0493, right? It keeps going, like the decimals keep going. I gave it to you as a PDF. You can also search it, Google Images. I like the one I gave you. Obviously, I gave it to you. If you don't like it, find a new one. Okay. Let's kind of break it down a little bit. Okay, the table lists proportions of the normal distribution corresponding to each z-score. And it even goes deeper than that. Okay. The A column is the list of z-scores. The B column lists the proportion in the body of the normal distribution for the z-score value. So that's the one you're probably going to look at first. Okay. So if the question is asking you, yes, find the z-score, and what is the proportion in the body, go for B. If the question is asking you about something in the tail, right? So usually it's asking for an outlier or for something that's smaller than like the bulk of the data, right? So think about the tail, go for column C. If it's asking you for a subsection, so something between like the mean and a score, okay, and I have some graphs I want to show you here coming up, go for column D, okay? So if it's asking you for just a straight z-score, A, that's a simple one. If it's asking you for like the bulk data, B, tiny data, C, in between data, D. Okay. So take a look at A first. Okay, so body, okay, is going to be anything that passes that median, that middle section. Anything greater than 50%. Anything less than 50% is going to qualify for tail. Sometimes the tails can be thick. Big guys. Okay. But again, tail, anything less than 50% technically qualifies as a tail. So 0.4999 can be a tail. It's weird, but it's a tail. Okay. So proportions of a normal distribution corresponding to a z-score of positive 0.25 and a z-score of negative 0.25. Yes, they're going to cross each other out. Okay. So take a look at A. So you see how in A, the shaded part, the body, corresponds to a z-score of plus 0.25. So it's just barely above the mean. That yields you a tail, if you're looking at the z table, if you're looking at that unit normal table. So look in tail, so C, 0.4013. The same exact z, just on the negative side now, negative 0.25. See how it kind of flips it? So now the tail, 0.4013, is on the opposite side. So the big takeaway with this one is watch the median. I understand we stop coloring. Most humans stop coloring, right? 3rd grade, 4th grade. It's okay. Color. Shade it in. Because what's going to happen is your brain is going to have to need to see how much is being taken up. How much space is that body being taken up, at least in the beginning. Shade it in. Okay? And the big takeaway is if the body crosses that median, if the shady part crosses that median, it's a body. If it doesn't, it's a tail. Okay. The unit normal table lists relationships between the z-score location and their proportion in a normal distribution. If you know the z-score location, you can look up the corresponding proportion. If you know the proportion, you can use a table to find the z-score. And yes, probability is always equivalent to proportion. Okay. Here's some more pictures. Let's look at A first. So if my z-score is z equals positive 1.00, and I'm asking you, what is the corresponding tail versus what's the corresponding body, right? You see how shading it in is going to be helpful? So this one, it's very clean looking, right? Z equals 1. So the shaded in part right there, that's the tail. It's very, very small. Okay, look at B. Z equals 1.5 or positive 1.5. C. Z equals negative 0.5. Okay. Tail versus body, tail versus body, tail versus body. Okay. So if you have your table out, get it out. If not, I don't know, I guess this is a video, you can still pause and then get, okay. Okay, find the proportion of the normal curve that corresponds to Z is greater than 1.50. I'll just give it to you because, again, this is a video. You can still pause it. Okay, proportion equals 0.0668. Okay, so use your table there. Do you see it? Okay. True, false. For any negative z-score, the tail will be on the right-hand side. Okay, so this might be helpful to draw it out. So draw a line. Draw a normal distribution for any negative z-score. So just draw a z-score on the negative hand side and then shade it in. The tail will be on the right-hand side. So if your z-score is over there, right, the tail is going to be on the left-hand side. If you know the probability, you can find the corresponding z-score. If it helps, read it backwards. If you know the z-score, can you find the probability? And so if you know the probability, you can find the corresponding z-score. Yes. Okay. The probabilities given in the unit normal table will be accurate only for normally distributed scores. Meaning, you can't use it on a skewed distribution. You need to verify that you're dealing with a normally distributed set of scores before you use the unit normal table. Okay. So here's your IQ scores again. So if the problem is to find the probability or proportion of the distribution corresponding to scores less than 120, what I need to do is I draw my distribution and I say, okay, I know that IQ scores, the average score is 100, standard deviation of 115, or standard deviation of 15. So I draw it there. Okay, my Z is 0, and then, okay, I have my standard deviation of 1. That corresponds to 15, so 115. So 120 is like slightly above 1 standard deviation. And if I look up my Z-score, right? I can find my Z formula. All right, my Z formula, remember, think back from last lecture. Z equals x minus mu divided by standard deviation. So 1.33, all right? Look where the body is, look where the tail is. Okay. These next two slides show you pictorially or graphically the difference between middle range, right, when you'd use a D column of your unit normal table, commuters, versus like the top range, or you use a tail, the C. Okay, so the middle range is, you see where that median is, or where that mean is, right? So we're saying, okay, the average commuter takes 26.1 minutes to drive to work, right? So if I'm looking for the middle 90%, what I'm doing is I'm chopping off the bottom 5% and the top 5%. So if I'm working in HR and I'm saying, okay, I want to look for like a drive reduction program, I care but slash don't care about people that walk to work, and I care slash don't care people that, I don't know, commute 3 hours to work, because I'm probably not going to really influence them to ever change, right? What I'm really doing is I'm looking at those middle 90%ers. And so before I even have that conversation with them, I need to determine how many minutes are they driving. So I run a statistical analysis and I'd find out, okay, the middle 90%ers at my company are driving between 9.5 minutes and 42.5 minutes, with the average being around 26 minutes. Okay, so that would be like the gold star from this kind of graph, versus, take a look at this one. Okay, these are my top 10%ers of my commuters. These are people driving more than 40 minutes a day to and from work. That's a totally different conversation to have with these people. Okay. Really quick, I want to talk about percentile ranks before I wrap up lecture. So the percentile rank of a particular score is defined as the percentage of people or individuals in your distribution with a score at or below that particular score. So when you talk about a percentile rank, you're going to use percentage, a number, right? And the percentile refers to a score. And what you're trying to do is you're using a percentage, but what you're really doing is you're giving a rank, like a rank order. You're giving I'm a better than or less than statement, but you're delivering it with a number. Okay. Quick learning check. Membership of Mensa requires, so Mensa is the international like Smart Persons Club. Okay. If you want to be part of Mensa, you have to take an IQ test. And to qualify, you have to score an IQ, you have to yield a test score of 130 or higher. And the one they use a lot is the Stanford-Binet IQ test. Okay. I think they're on version 5 or whatever. Okay. So again, IQ average is 100, standard deviation 15. So knowing this, what proportion of the population are they looking for? Right? So if you know they're looking for the people that score 130, and the average score is 100 with standard deviation of 15, okay, so 115, 130, right? And again, anything that you can turn into a proportion, you can flip into a percentage. Okay. They're looking for the top 2%ers. And they get together usually once a month. Talk about smart people things. Okay. So just a quick peek into looking ahead. So many research situations begin with population. Absolutely, humans, regardless of the topic, we form ourselves into an interval distribution. We can't deal with the population because of resource allocation considerations, so we deal with a sample. We grab a sample and then we administer a treatment. We do a study with it. And then we use probability to decide, okay, we did this treatment on a sample and it yielded a result. Was that result noticeably different? If it is, great, let's run it again, see if we can replicate it. And then if we can, let's push it back out to the bigger population. Okay. Any values that are extremely unlikely to be obtained just from the original population are viewed as evidence of the treatment effect. Okay. If it falls in the middle range, we're not going to treat it like as anything special. We're not going to treat it as evidence of treatment effect. But if we do something to that sample and the scores are now like wildly different, if they're extreme, if they're now considered like outliers, well then yeah, now we do consider that evidence. Now we have something to go back to our funding source and be like, well, yeah, can we use this now, right? So, and again, z-score is just another tool we can use, and probability is using z-scores in a way to couple that with probability. So yes, I'll leave you with probability as a powerful tool, and z-scores places exact distances from average. And if you can, as the researcher, right, manipulate that independent variable, and you can create a treatment and change it in such a way that it's noticeably different, you can prove treatment effect, and that is powerful.